Bismillahirrahmanirrahim. Nous allons avoir l'honneur d'assister à la soutenance de thèse de doctorat de 3e cycle réalisée par M. Nijkhioui Oussama, portant le titre de, je vais le dire en français, étude expérimentale et numérique d'une poutre en béton armé renforcée par des matériaux composites. Une toute petite présentation de M. Nijkhioui Oussama, tout juste pour dire que M. Nijkhioui est titulaire d'un master en génie civil, spécialité structure, obtenu à l'université de Médéa, et que les travaux réalisés dans le cadre de ce doctorat ont été rédigés dans un mémoire de 110 pages, un petit peu spécial, puisqu'il a été entièrement rédigé en langue anglaise, et ce n'est pas très courant, franchement. Donc ces travaux ont fait l'objet d'un article paru en septembre 2023 dans la revue Structure, qui est une revue de rang A, quand même, c'est tout à l'honneur du candidat. Revue éditée par Elsevier. Ces travaux, donc cet article a été rédigé en collaboration avec professeur Rafik Madi et professeur Mohamed Gamfoud de l'université du 45 et du professeur Mohamed Nijkhioui du laboratoire matériaux et environnement de l'université Yahya Fars de Médéa. Avant de donner la parole à M. Oussama Nijkhioui, je voudrais informer l'assistance que les travaux réalisés dans le cadre de cette thèse vont être exposés devant les membres du jury suivant. À ma gauche, les examinateurs, professeur Nafa Zahardine de l'université du 45 de Guelma, professeur Bouzien Saleh, examinateur également de l'université de Skikda, et à ma droite, nous avons professeur Madi Rafik, encadreur de ce travail, et professeur Gamfoud Mohamed, invité, tous deux universités du M45 Guelma, et moi-même, professeur Ben Malik Mohamed Harbi, président de ce jury. Monsieur Oussama Nijkhioui, si vous êtes prêt, nous vous donnons entre 30 et 40 minutes pour exposer votre travail. تفضل مشكور.
بسم الله الرحمن الرحيم. السيدة رئيس اللجنة، السادة أعضاء لجنة التحكيم، حضوركم شرف لنا. I'm delighted to welcome you to today's presentation on experimental and numerical study of a reinforced concrete beam strengthened by composite materials. Before we begin, allow me to introduce myself. My name is Oussama Nijkhioui, and my supervisor is Professor Rafik Madi. My study field is civil engineering, and my specialty is structures. I'm a PhD student at Guelma University. I'm excited to share insight into the fascinating work of a reinforced concrete beam strengthened by composite materials. And we'll explore today together how we can enhance the load-bearing capacity and the durability of these structures. We'll start by introducing our research goal and context. Then we'll talk about composite materials and why they are important. Next, we display how we conducted our study. After that, we discuss our findings and show them on both experimental and numerical analysis. And finally, we wrap up by summarizing the main points or extruded for our study. Starting by the introductions. The field of civil engineering balances innovation with tradition, continuing adapting to modern needs while ensuring structural safety. Key to this study is the design and analysis of the reinforced concrete T-beams. essential for supporting various infrastructure elements. However, incorporating opening in reinforced concrete structures, while a significant advancement, presents challenges to their strength and stability. In the realm of reinforced concrete structures, traditional methods of repairing, such as lining degraded components with concrete, have limitations like increased weight and downtime during repair. Hence, exploring alternative retrofitting strategies like fiber reinforced polymer is crucial. This study aims to investigate how longitudinal rectangular opening influence the flexural behavior of reinforced concrete T-beams and assess the effectiveness of FRP materials in strengthening and retrofitting of the reinforced beams, as well as evaluating the mechanical properties and adhesion with concrete substrates. Moving on to the composite material. What is a composite material? A composite material is made of two or more materials with different mechanical properties. It is used to enhance its base materials. In our study, we used carbon fiber reinforced polymer. So what are the components of these materials? This picture shows the FRP components. Fiber reinforced polymer composite consists of two primary components, fiber and polymeric matrix. Fiber refers to a slender, elongated materials that serves as the primary load-bearing constituents within the composite, commonly made of materials like glass, aramid, or carbon. Matrix facilitates load transfer between fibers, ensuring directional stability, as polyester, vinyl ester, and epoxy. Adhesion between fiber reinforced polymer and concrete substrate is crucial for effective strengthening. Requires close attention, requires close contact and absence of weak layers or contaminations. The behavior of a reinforced concrete beam strengthened by FRP materials. The following curves show the behavior of strengthened and unstrengthened beams. Using composite materials, specifically fiber reinforced polymer, bonded with epoxy adhesive on tension or lateral surface, is an effective way to strengthen beams, especially those weakly reinforced. Bonding FRP materials to tension surfaces increases the ultimate strength and stiffnesses, limiting crack propagation and corrosion, thus enhancing their durability. Moving on the methodology. We will discuss in this section the characteristics of the material used as concrete, steel, and CFRP, the process of the beam manufactures, the CFRP and strain gauges installations, and finally the test instrumentation and test setup. Before we start, let me shed a light on the precise process we followed in manufacturing our tested beam. All the beams were made up at the Laboratory of Civil Engineering and Hydraulics LGCH at Gilmer University. We carefully followed a consistent production process, paying close attention to every detail, from mixing, pouring, vibration, and storage, to reduce any outside influences that might affect our test outcomes. Starting by the characteristic of the material used. Our concrete mix comprised a CPG CM2 L42.5 cement sourced from natural soil, along with the gravel 515 from Busello Afjud Kari, and the rolled sand L5 from Oman. The following table shows the mineral composition of our cement and the physical characteristic of the sand and the gravel used in our study is shown in this table. To determine the concrete piece proportion, we employed a Drogolis formulation method. The Drogolis method is a reliable technique widely used in concrete determination composition. After casting cylindrical specimens, we conducted a completion test, which revealed an average complete compressive strength of 21.5 megapascal at 28 days. The following table shows the proportion of the material required to achieve this compressive strength. Moving on the steel bar reinforcements. We use identical 8 mm diameter bars for the tension zone, 8 and 6 mm for completion zone, with 11 vertical stirrup of 6 mm diameter and 100 mm spacing along the beam. These bars were carefully tested under tension to find out their mechanical properties, including yield strength, ultimate strength, flow modulus, and the elongation, as it is illustrated in the following table. With concrete and steel bar reinforcements, we incorporated a composite material, CFRP, for external retrofitting and strengthening our tested beam. We use unidirectional CFRP laminate from Sikar-Carbonate S1012 with its appropriate epoxy resin adhesive from Sikar-30, both with mechanical properties illustrated in this table. The beam manufacturers. 18 reinforced concrete T-beam were made with identical dimension and steel bar reinforcement. All the beam had the same length of 1,100 millimeters with the same sections of 100 millimeter wide and 160 high. The flange of each beam was 250 millimeters wide and 50 millimeters high. The longitudinal opening was created by passing the foam materials with the cross sections 3 times 40 along the beam. And while it strategically positions under the neutral axis, this design choice has a significant impact on the structural behavior, and understanding its rationale is key to interpreting our result accurately. Our tested beam were divided into 4 groups. The first is for the control beam, and this beam were not strengthened in the tension zone. The second is for the strengthened beams, and the strengthened beam were strengthened by 1 CFR laminate on the tension zone. The third is for the preloaded beam, by 80% of the ultimate load control beam, and after that they are retrofitted by 1 CFR laminate on the tension zone. And the last group is like the third one, but in this case, the beam were loaded by 100% of the ultimate load of the control beam. The process didn't end with the manufacturing, so we need to apply the CFRP laminate to the complete surface. And to do that, we must cut the CFRP to the required length and clean with solvent to remove dirt and dust. Then a thin layer of adhesive was applied to both the complete surface and the clean CFRP laminate surface. After that, the CFRP laminates were placed on the complete surface and tightly pressed using a rubber ruler to avoid air bubbles. The strain gauge installations. Strain gauge on the reinforcement bar. To install the strain gauge on the reinforcement bar, we first need to prepare the surface of the bar to ensure good contact between the bar and the gauge. This is done by removing any excess strips using a grinding machine. Then we clean the surface of the bar to remove dirt and dust. After cleaning the bar, we apply the adhesive on the bottom side of the gauge and in the exact location of the bar. Then we press the gauge into the adhesive and force out air bubbles. Then we apply tape under the exposed electrical wires, because these electrical wires must not touch the rebar definitely. Then we cover the gauge with the waterproof and corrosion resistant materials. And finally, we check electrical connection, because to ensure that the gauge is working correctly. Complete and CFRP strain gauge. The same process followed in installing strain gauge on steel bars must be followed in installing the strain gauge for concrete and CFRP laminates, as you can see in the following pictures. Finally, our test instrumentation and setup was carefully designed to conduct a 3-point bending test. The 3-point bending test conducted on simply supported beam with mid-span loading and 900 mm clear spacing. Strain gauges and LVDTs used to measure strain and mid-span displacements with the load control method applied using a hydraulic actuator. Moving on to the results and discussions. In this segment, we shift our focus on the empirical findings derived from the experimental phase of our study. Our experimental phase conducted to evaluate the crucial parameters as first cracking load and ultimate load, the failure mode, the load deflection behavior, and the load strain behavior. Starting by the first cracking load. The following graphs show the first cracking load gain of all the tested beam. We observed significant differences among the various types of beam. For instance, the presence of a hollow core in the beams resulted in a reduction of the first cracking load by 24% compared to solid beams, as you can see in the first column. However, a remarkable increase in the first cracking load of retrofitted and strengthened beam was observed. Moving on the ultimate load, the following graphs show the ultimate load gain of the all tested beam. We found that all strengthened beam or retrofitted beam displayed higher ultimate loads compared to the control beam. The ultimate load of hollow beams decreased slightly, attributed to the reduction in flexural rigidity caused by the hollow core. Moreover, we observed that the higher ultimate load was observed in the preloaded beam by 100% of the ultimate load control beam, owing to the dispersion of compressive and shear stresses between the CFRP laminates and concrete. These results indicate the effectiveness of CFRP laminates in enhancing the beam's flexural rigidity. The following pictures shows the failure mode of control beams, the solid in the right and in the left and the hollow in the right. A same crack propagation pattern was observed in both solid and hollow beams. The crack appeared in the concrete tension zone at the middle of the beam, followed by oblique cracks along the sides, gradually increasing in thickness and length until reaching the concrete compression zone at the flange, resulting in a flexural failure, as you can see. The failure mode of the strengthened beam are shown in the following pictures. A different crack propagation and failure modes compared to control beam was observed. The crack initiated from the upper center of the beam and progressed diagonally towards the support, leading in failure due to concrete cover separations. In this case, we noted that the amount of the concrete cover separation was greater in hollow strengthened beam compared to solid strengthened beam, due to the higher ultimate load carried by this hollow beam, with a lower moment of inertia than the solid beams. The following pictures show the failure mode of the retrofitted beams. A similar crack propagation and failure modes for the strengthened beam was observed, compared to strengthened beam. The retrofitting with CFRP induced a new crack pattern and delayed the appearance of first cracks, which rendered the beam unaffected by initial cracks created from loading in the failure mode. This indicates the significant influence of CFRP strengthening and retrofitting on the crack propagation and failure behavior in reinforced concrete beams. Moving on to the load deflection curve behavior. The following curves show the load deflection curves for controlled and strengthened beams, the comparison between them. We can divide the behavior of the load deflection of the beams in 3 stages. The first from the beginning to 10 kilonewton. In this stage, the concrete remains anchored, and all materials display linear elastic behavior with uniform stiffnesses. From 10 to the yielding strength, controlled beam exhibits decreased stiffnesses compared to strengthened beam due to the appearance of initial cracks in the concrete zone. The hollow beams demonstrated slightly reduced stiffnesses compared to solid beams, attributed to the longitudinal opening, indicating higher ductility. Upon reaching the yielding load, I mean at 35 kilonewton, the strengthened beam experienced significantly reduced deflection compared to control beam, indicating the load carrying capacity of CFRP, with a reduction about 45% respectively. While controlled beam experienced plastic deformation until failure, the strengthened beam exhibit the appearance of the first crack due to the CFRP strengthening, leading to a slight decrease in stiffnesses compared to controlled beam deflections. The maximum deflection of strengthened beam decreased by about 77 and 71% respectively compared to controlled solid and controlled hollow beams, highlighting the higher rigidity of CFRP strengthened beams. While CFRP strengthening significantly enhances stiffnesses and reduces deflections, it's crucial to maintain ductility to avoid premature debonding. As solutions, we can use the shear strengthening and anchorage systems. Here are some examples of anchorage systems and shear strengthening to avoid the premature debonding of the beam. The following curves show the load deflection curves for the retrofitted beam. A similar load deflection response was observed compared to strengthened beam. The following curves show the steel strain in control beam. The maximum strain on the steel bars in control beam, in control solid beam, was higher than that of hollow beams. This can be attributed to the control beam's ability to support a higher load, generate higher moment in the beam, thus resulting in more strain on the steel bars. All the longitudinal steel bars yielded after the yielding load. The steel strain increased rapidly due to the loss of the material resistance properties in the plastic region. The concrete strain in control beam was shown in the following pictures. The concrete in compression zone also experienced higher strain in control beam, in solid beam compared to hollow beam, for the same reason in the steel bar reinforcements. The following curves show the concrete strain in strengthened beams. Concrete strain was significantly reduced in the strengthened beams, both solid and hollow one, decreasing by 84 and 58% compared to control beams. This indicates the effectiveness of CFRP laminate in reducing concrete strain and preventing excessive deformation or cracking. the maximum concrete strain in strengthened hollow beam was greater, emphasizing the impact of the moments of inertia on strain distribution. The maximum steel strain of the strengthened hollow beam was lower compared to strengthened solid beam due to the high resistance of steel bars in the strengthened solid beam against the higher load. The following curves show the steel strain in preloaded beam. A similar trend in the load strain curves of the retrofitted beam compared to the strengthened beam was observed. Moving on the load strain of CFRP materials. All the CFRP load strain of the tested beam show clearly that the linear stage of the CFRP materials was not exceeded to the sudden concrete failure. The maximum CFRP strain was lower in hollow beams compared to solid beams, attributed to the differences in load distribution and resistance. The numerical analysis. We began our study by conducting experiments, but due to the challenges and costs of these experiments faced, we opted for a new approach, numerical simulations. We discussed in these sections the finite elements modeling, material modeling, validation of the finite element model, and the parametric study. Let's start by the finite element modeling. We constructed a 3D finite element model in Abacus to simulate the behavior of the tested beam. The concrete materials was represented by linear brick elements, as was steel by linear truss elements. The CFRP laminate was modeled by shell with 3 layers with different directions. Validation of the finite element models. The following curves show the comparison of the experimental and the numerical curves of the load deflection curves. The load deflection curves obtained through numerical simulations are closely matched to the experimental data. This indicates the reliability of our numerical model in predicting the behavior of the tested beams. Moving on the parametric study. We conducted in our parametric study the effect of the longitudinal opening position, opening side, and shear strengthening using different CFRP wrapping configurations. As the position of the opening moves away from the neutral axis, the negative effects of the beams increased, as you can see in the following curves. As the size of the longitudinal opening increases, the negative effect of the ultimate load and the ultimate deflection also increases. After strengthening this beam by CFRP laminate on the tension zone, a significant increase in the ultimate load capacity on the strengthened beams was observed, as you can see in the following curves. To avoid a premature debonding, we employed a shear strengthening. The shear strengthening with CFRP wrapping configuration resulting in an increase in ultimate load capacity and improved their ductility, as you can see in the following pictures. Finally, the conclusions. The longitudinal openings negatively affected the first cracking load, but CFRP laminates enhanced it in both solid and hollow beams. CFRP strengthening significantly improved the ultimate load, especially for higher preloaded beams. The failure modes differed between unstrengthened and strengthened retrofitted beams, with CFRP enhancing rigidity and reducing strain on concrete and steel. The size and location of the longitudinal opening greatly influenced the flexural behavior and the effectiveness of CFRP. The European configuration of CFRP along the cruise plane of the beam demonstrated optimal performance in terms of ultimate load and ductility. And here some additional informations. We have published one publication for titled by Structural Behavior of Hollow Reinforced Concrete T-beams Strengthened on the retrofitted with Carbon Fiber Reinforced Laminate Experimental and Numerical Investigation in Journal of Structures, and 2 international conference and 2 national conference. And thanks for your attention.